about a minute and then we begin, okay? Okay, do you guys think I should begin? Should I go?
Yeah, go ahead.
Okay. All right. So thank you again, everybody, for joining this session of virtual seminars in economic theory. Today we have Alexander Bloedel from Stanford, who's going to present the cost of optimally acquired information, which is joint work with Weijie Zhong, and he is also here with us. And we're also very pleased to have as guest panelists Andrew Caplin and Philipp Strack. As you probably already know, the format is a 60-minute presentation with a 50-minute session for questions and discussion at the end. Please keep your microphones muted during the talk, but you can ask questions in the chat, and then there will be an opportunity to ask questions in the Q&A session at the end. Let me remind you that the talk is recorded. And before I hand over to Alex, we do these seminars every Thursday at 4 p.m. UK time. And next week we'll have Arjada Bardi from Duke, who present local evidence and diversity mini publics with Nina Bokova. And the guest panelist will be Steve Callender. You can find more information on our website, or you can follow us on Twitter. Thank you, Alex. The microphone is yours.
Great. So first, thank you to the organizers for the invitation, and thank you to Andrew and Philip for being here as panelists. And I'll just reiterate that this is joint work with Weijie, and he's here to answer questions in the chat. So the main question of this paper is, how should we as economists be modeling the cost of information? And in particular, our goal is to help other economists who want to model costly information acquisition by providing guidance on what constitutes a good or a reasonable information cost function. Now, very briefly, our high-level motivation for this is the observation that information is a key input to basically all economic decisions, and people choose what information to hold by trading off the value that it confers through better decisions against the cost required to obtain it. And these costs could correspond to the expenditure of physical resources, to cognitive effort, or to money. And in recent years, a large and growing applied literature has studied endogenous information choice in a range of important economic applications. And this literature has generated a growing set of examples illustrating that fine details of the way that we model information costs can have important implications for the economic predictions that our models make. So it's important to get the cost side of things right. Let me outline the basic decision problem that we study. So there's a Bayesian decision maker, DM, who faces a one-time decision under uncertainty. She has a prior belief P over an uncertain state theta, and she can acquire information in the form of Blackwell experiments sigma that generate signals S whose distribution depends on the true underlying state. Canonical examples of experiments include partitions of the state space or signals that are equal to the state plus Gaussian noise. And the cost of each experiment is determined by a cost function C, which might also depend on the prior. So the decision maker first chooses an experiment, then observes the realized signal, and finally takes a signal contingent action. And this is all done in the service of maximizing her expected utility from the action, net of her cost of the acquired experiment. Now, in such environments, the value of information is unambiguous. It's completely pinned down by the utility function and by the action set. The question that we address in this paper, which has remained largely open, is the complementary one, namely, what constitutes a good cost function? Are there particular properties that this cost function C should satisfy no matter what the economic context is? And should we be using particular functional forms for use in specific economic settings? So to date, the literature has taken basically two distinct approaches to this problem. The first goes back to the seminal work of Chris Sims on rational inattention and posits a particular functional form called mutual information. This has become very popular because mutual information is highly tractable and also has micro foundations in information theory. However, it's also been widely criticized on the grounds of being ad hoc and generating unreasonable predictions in some economic applications. More recently then, a newer literature has taken a second approach, which basically goes back to first principles and tries to derive particular functional forms by starting with an abstract cost function C and imposing interpretable axioms on it. So a good example of this is a recent paper by Philipp and his co-authors, which basically imports the classic idea of constant returns to scale from producer theory into this informational context and derives a particular functional form. The approach that we take in this paper is in some sense closer to the axiomatic one, but differs in that we consider the meta-axiom, if you will, of optimality. And in particular, we study the kinds of cost functions that can be rationalized by some underlying optimization process in which the decision maker chooses not only which experiment to acquire, but also can flexibly choose how to acquire her chosen experiment. So I'll unpack this over the next couple of slides. But quickly, to draw a loose analogy to producer theory, if we view experiments as output bundles and information gathering strategies as input bundles, basically our exercise is a classic one of rationalizability. In other words, we characterize the kinds of cost functions that are rationalizable under a particular richness assumption on the underlying production set for experiments. Okay, so what does all this mean? In the decision problem that I described, and this is consistent with a large majority of economic applications, information choice is modeled as a one-shot decision. But in reality, decision makers, once they choose which experiment to acquire for decision-making purposes, have a lot of flexibility in choosing strategies for gathering that experiment. So surely the decision maker can acquire an experiment directly in one shot, but she can also do more. First, she could acquire a more informative experiment and then simply ignore the extra information that isn't needed for her decision. She could also engage in mixed strategies by randomizing between multiple experiments. And most substantively, she could also design a sophisticated sequential strategy that in some sense adds up to the information that she wants to acquire, where the experiments chosen at later steps of the sequential process can be made contingent on signals generated at earlier steps of this process. So for instance, an online consumer doesn't need to commit upfront to how many product reviews she'll read before making a purchase decision. Instead, she could economize on reading costs by choosing to stop early if the first few reviews are very informative. For instance, if they're all 5-star reviews or if they're all 1-star reviews. And what this means is that rational decision makers are actually solving a much larger optimization problem, where they first choose which experiment to acquire, that is, what information to learn. And then conditional on that, they also choose the optimal information gathering strategy by optimizing over these above dimensions. In other words, they choose how to learn their chosen experiment. Now, in order to focus purely on the cost side of things, in this paper, we focus on this inner optimization problem over how to acquire a given experiment for each such experiment. Now, these considerations give rise to a kind of modeling tension. On the one hand, in many settings, optimality in the sense of minimizing total expected costs requires gathering information sequentially. This is true in many settings. Examples include sampling from a population, as in statistics, encoding data into strings of zeros and ones for transmission or compression, as in information theory. And there's also a large body of evidence in psychology and neuroscience that real humans in lab experiments process information gradually in a sequential fashion. So an ideal outcome might be for us to explicitly model the entire dynamic process of information gathering. On the other hand, static models are extremely convenient for a number of reasons. One is that they're inherently simpler and more tractable, which is important for applications. Another is that in many settings, it's hard to directly test dynamic models because we don't actually observe the process by which information is gathered. And finally, many economic models have a kind of atemporal structure in the sense that while we care about the final outcomes that are realized, we don't necessarily care about the process by which those outcomes are generated. So in essence, what we do in this paper is propose and then study the implications of a resolution to this tension. And the basic idea is that we should use static models for convenience, but the cost functions that we use in these static models should be disciplined by the fact that the agents in these models have access to larger sequential strategy spaces. Now, there are at least two ways to formalize this. One is to use cost functions that are robust to the possibility of sequential learning, in the sense that they make it so that learning everything in one shot is weakly cheaper than following some sequential strategy, even though sequential learning is feasible. The second way to formalize this is to accept the fact that agents in our models are in fact learning sequentially, but to model this in reduced form in a static way by using cost functions that are the value functions, if you will, of the agent's sequential optimization process without actually modeling that process. So with this background in mind, we do three things in this paper, starting with the most general and working towards the most specific. In the first part of the paper, we propose two new criteria for what constitutes a good information cost function. And these closely mirror the two resolutions that I just described. First, we say that a cost function is sequential learning proof, or SLP, if, roughly speaking, one-shot learning is without loss of optimality. Second, we envision the decision maker as starting with some primitive cost function over one-shot experiments, which we call her direct cost. She can then design any sequential strategy with the flow cost at each step of the strategy given by the direct cost function. Minimization over sequential strategies then generates a reduced form value function, which we call her indirect cost. And the first theorem of the paper says, in essence, that these two notions are equivalent. A cost function is SLP if and only if it's the indirect cost generated by some underlying direct cost. And this equivalence then gives us license to ask two closely related rationalizability questions. First, if you hand me a given cost function, is it SLP? If it is, then you're good to go. If not, then the agent in your model would optimize away some of its features, so you might want to rethink the model that you've written down. Second, for each SLP cost function, what is the full set of direct costs that could have generated it? And the answer to the second question can shed light on the economic assumptions that are being made when you write down particular functional forms for the SLP or indirect cost in your model. In the second part of the paper, we then use this framework to provide micro-foundations for the so-called uniformly posterior separable, or UPS cost functions, which were first introduced by Andrew and co-authors, and which these days are basically synonymous with the modern rational inattention approach. We present two characterization theorems. The first says that a cost function is UPS if and only if it's SLP and also satisfies a seemingly mild smoothness condition that we call regularity. This provides apparently compelling foundations for the UPS model. The second theorem then says that a cost function is UPS if and only if it's an indirect cost, and moreover, every underlying direct cost that could have generated it satisfies a property that we call preference for incremental learning. Basically, what this means is that the optimal sequential strategy involves observing only Gaussian diffusion signals in the continuous time limit. And this is economically restrictive because it rules out the strict profitability of ever acquiring information in large chunks. So the main takeaway from these theorems is a kind of choose your own adventure for applied theorists. If you're an applied theorist and you want to do what people in the rational inattention literature are already doing, but you need to get a critical referee off of your back, you can cite the first theorem and say, well, I want my model to be internally consistent, so I need SLP. And for tractability, I need some smoothness. And that means all of that I'm left with is the UPS model. The second theorem, however, says that if you're interested in more than just applications, you might want to think more critically about whether these smoothness conditions are warranted in your particular context, because they are economically restrictive. Finally, in the third part of the paper, we use this framework to refine and reinterpret other normative axioms that have received attention in the literature. This allows us to, among other things, speak to some recent modeling debates in the rational inattention literature. Now, in the interest of time, let me defer an explanation of what these results say to the end of the talk. For now, I'll just quickly mention that one of these axioms, which is called compression invariance, is inconsistent with our notion of sequential learning proofness, and in an even stronger sense is inconsistent with the UPS model. On the other hand, the latter two axioms, constant marginal cost and compression invariance, when taken in conjunction with sequential learning proofness, uniquely pin down particular functional forms, which we think are particularly tractable and might be of use in economic applications. And I should also note up front that these latter two characterizations are closely related to some recent papers by Philipp and Andrew and their co-authors. And I'll discuss this as we go along. Okay, so this is a diagrammatic representation of what we do in the paper, with the left-hand panel here representing the first two parts and the right-hand panel representing the third part. So this is a good place to pause for high-level questions if there are any.
I don't have a question, but I have a comment, which is it's very clear-headed, and the analogy with production theory is so strong that I don't think there's a single approach to production theory that won't be mirrored ultimately in the theory of learning.
Great. Perfect. I'm glad to hear that. Okay. So let's just quickly get to the model. Briefly related literature. I've already mentioned that there's some work that looks at axiomatic foundations for information costs. We differ from this work in that we focus on optimization. There are two closely related papers, one by Philipp and Stephen Morris, and another by Ben Hebert and Mike Woodford, that provide related sequential sampling foundations for UPS costs. I'll discuss these more later. The main difference is that those papers consider much more constrained versions of the optimization problem that we consider, and therefore derive special cases of only one direction of one of our UPS theorems. A bit more distantly, UPS measures can be microfounded alternatively as the value of information for Bayesian decision makers. This is complementary to the cost-based approach. There's also a large revealed preference literature in which Andrew features prominently, which, unlike our approach, treats the cost function and the information that the decision maker acquires as unobservable, and instead tries to infer those things based on observable choice behavior in different decision problems. And finally, there's a large and long literature on dynamic information acquisition, the aim of which is to explicitly characterize the optimal dynamics of learning. And this is, of course, different from what we do because we focus on the reduced form static implications for indirect cost functions. Okay, so here's the plan. First, I'll lay out the framework and tell you about sequential learning proofness and indirect costs. Then I'll spend most of the time talking about our theorems for the UPS model. Then, time allowing, I would like to at least sketch what we do in the third part of the paper, although perhaps we'll have to defer that to the discussion section at the end, and then I'll briefly conclude. Okay, so the model. This is basically what I've told you already, but now with just a little bit more notation and a little bit more precision. There's a finite set of states theta. Information about these states is represented as Blackwell experiments sigma that generate signals S whose distribution depends on the true state. The decision maker has a prior belief P, and the Bayesian posterior conditional on a signal S is denoted by this Q of S. And it's well known that each experiment and each prior induce a random distribution, a distribution for the decision maker's random posterior, and this distribution will sometimes be denoted by pi. Now, for technical reasons in the paper, we impose some additional technical conditions. I want to gloss over these for the most part, but there are two pieces of notation here that are going to show up. First, we restrict to prior beliefs that have full support, and the simplex of full support priors is denoted by delta naught. And second, we restrict to experiments that are bounded in the sense that they induce log likelihood ratios that are almost surely bounded. And the space of bounded experiments is denoted by this script E sub B. A cost function is then a map C that assigns non-negative real numbers to pairs of bounded experiments and full support priors. And we require that a cost function satisfies just 3 conditions. First, Blackwell equivalent experiments should have equal cost. This just means that the cost of an experiment depends only on its information content. Second, a completely uninformative experiment has 0 cost. And third, these cost functions satisfy technical continuity condition that, again, I'll gloss over unless there are questions. And the space of all cost functions is denoted by this script C.
Alex, not a question, but a comment. I'm sure that nasty stuff could happen if you found yourself heading toward a boundary. And I would imagine that's a large part of what you have to get rid of in the cost area. Infinite
Yes.
derivatives happening in strange places.
Right. Yeah. So there are 2 properties of a cost function at boundaries that might be problematic. One is like mutual information. The derivative of the cost function might become infinite. That's actually not going to be problematic for us. The other feature that causes some technical headaches is when the actual level of the cost becomes infinite near boundaries. So, for instance, the cost function from Philipp's paper with Omer and Luciano has the property that the cost of a completely informative experiment is infinite. And when we do sequential optimization, this causes some technical headaches. And so restricting to bounded experiments allows us to get around that. There's also the conceptual point that when your prior belief only has partial support, there's the question of whether costs should depend on the actual signal distributions or whether it should depend on the distribution of induced posteriors. And restricting to full support priors and bounded experiments allows us to completely sidestep that for the most part. But these are mostly technical concerns.
I mean, in some sense, one should expect that a regularity assumption is necessary here, no? Because I could just assign infinite cost to some set of experiments in principle, and I can approximate this in a kind of way where I don't assign infinite cost, but I just make them grow fast enough. So some.
Yeah. That's exactly right. So we are requiring some finiteness here. We are requiring some continuity, but by the Tights extension theorem or whatever else, you can approximate basically any shape for the cost function arbitrarily well.
May I ask a question here? Just for a second. So just to go back to that again. So it sounds like you have an infinitely rich set of feasible experiments, where feasibility means finite cost bounded from above.
Yes.
Mm-hmm. And do you think of that as a restrictive assumption?
Yeah. So this is a great question, which I think applies more broadly to the sort of broadly defined rational inattention literature. Should we give decision makers complete flexibility in what to learn, or should we restrict them to particular parametric classes? On one hand, I'm happy to acknowledge that this is a perhaps extreme assumption, although it's a useful one to not a priori restrict what kinds of information can be acquired and instead let the decision makers in our models choose that endogenously. And second, in line with the question that Philipp just asked, we're imposing few enough assumptions on these costs. For instance, they don't need to be monotone or anything like that, so that we could set the cost of particular subsets of experiments to be well-behaved and finite, and roughly speaking, allow the cost of all other experiments to grow very, very quickly and have a very, very high value, so that they're effectively infeasible.
I think the question was of the opposite nature, which is this is a lot of experiments, so let's keep it going. That's a lot you're allowing. Anyway,
okay.
Maybe I misinterpreted.
Yes. So at this stage,
I think he answered it sort of with that interpretation.
Okay. Yes. So we are assuming a kind of richness on the feasible set of experiments, but we're imposing basically no assumptions on what the cost function can look like at this stage. Okay. So now to the main definitions. we say that a cost function C star is sequential learning proof, or SLP, if, roughly speaking, it's cheaper to acquire information in one shot than via any two-step strategy. Formally, and this requires some notation, a cost function is SLP if it's the fixed point of this two-step operator, psi, that maps cost functions to cost functions. And the way it works is as follows. You start with some target experiment sigma that you want to acquire. In a first step, you acquire first stage experiment sigma 1. You then observe the realized signal and update your belief accordingly. And contingent on that signal, you can also choose a second stage experiment. And this operator infamizes over all such two-step processes, subject to the constraint that the total amount of information generated by the two-step process is sufficient for the experiment that you want to acquire in the Blackwell sense. So basically, this is taking the lower envelope over two-step strategies, and sequential learning proofness just means that the cost function is a fixed point of this process. So here's the simplest example to illustrate this. Suppose you want to model a consumer who's deciding whether or not to buy a product that can be of low, medium, or high quality, and she can acquire some information before making this choice. And the cost function that you specify says that it costs $1 to generate any binary partition of the state space. So for instance, to separate low quality from medium or high, or to separate medium quality from low or high. And similarly, it costs $2 to perfectly learn the state. So the first question is this cost function internally consistent? And our answer is, well, no, it's not sequential learning proof. So a rational decision maker would optimize away some of its features. And to see that it's not SLP, note that the cost of perfectly learning the state, $2, is strictly greater than the cost of the two-step strategy, where the decision maker first separates low quality from medium or high. Conditional on seeing that it's of low quality, she stops learning. And conditional on seeing that it's not, she then learns whether it's medium or high quality. So the natural next question is, since this cost isn't SLP, what reduced form cost function would the decision maker end up with after running this cost function through sequential optimization? This is where the second definition comes in. The decision maker starts with a direct cost C, which doesn't need to satisfy any assumptions other than those that I've already told you. She can then design an arbitrary sequential strategy with the flow cost at each step given by the direct cost, and minimization over these strategies generates what we call her indirect cost, C star, which is sometimes denoted by this operator phi. Okay, so what is the strategy space that she's optimizing over? Well, she starts with a target experiment sigma that she wants to implement. And then we say that a 2t period sequential replication consists of the following pieces. First, there are signal spaces for each of the 2t periods that satisfy some technical conditions. Second, in even periods, there are experiments sigma that add new information about the state. And third, in odd periods, there are garblings gamma that basically discard information about the state that had been acquired in previous stages. And the replication constraint, I should say, I'll comment on garbling in a moment. And the replication constraint is that the terminal signals that are generated at the end of this process should be Blackwell equivalent to the target experiment that's being replicated. So some things to note here. First, the decision maker only pays for the experiments in the acquisition rounds, which captures the idea that information in the odd rounds can be freely disposed of if she so chooses. Second, beliefs are only updated on and experiments are only conditioned upon information that hasn't been discarded up to that point. And finally, part of this optimization is choosing the time horizon. So in effect, by sending the time horizon to infinity and simultaneously scaling down the amount of information that's acquired at each step, this model is sufficiently general to allow us to take well-defined continuous time limits. Okay.
Could I ask one question about the garblings?
Yes, please.
Could you explain a little bit more why they're necessary? And would they be necessary if you impose something like Blackwell monotonicity on the cost?
Perfect. Yeah, so I was going to get to this on the next slide, but I'll just answer now. So So these garbling rounds are going to be necessary to guarantee that the indirect cost is Blackwell monotone, meaning that it's weakly increasing in the informativeness of experiments. Perhaps surprisingly, you can construct examples where without this kind of garbling, you can start with a Blackwell monotone direct cost and end up with a non-Blackwell monotone indirect cost. The basic idea is that in a sequential setting, acquiring information in a given step serves two roles. One is that it works towards generating the total amount of information you need to get your target experiment. And the other is that information at earlier stages can help you refine your search process later on. So there are instances in which that second effect actually outweighs monotonicity of the direct cost, so that it's cheaper to acquire more information than you actually need for your target experiment. But if we were to get rid of these garbling rounds, everything aside from Blackwell monotonicity would go through, and in fact, everything in subsequent sections of the paper would go through effectively verbatim. But we think monotonicity is an important property, so we build it in. Thanks, very good question. Okay, so theorem 1, as advertised, is a sanity check that says these two definitions are equivalent. In particular, a cost function is SLP if and only if it's its own indirect cost, meaning it's a fixed point of the full-blown phi operator, if and only if it is the indirect cost generated by some direct cost. Now, the equivalence of points 1 and 2 here is basically just the one-shot deviation principle, so isn't terribly surprising. But it's often much more convenient to focus on SLP rather than indirect costs, because SLP only involves two-step strategies, and these are it's a much smaller space. Perhaps more surprising is the fact that 3 implies 1 and 2. In other words, starting from any direct cost, you get to an SLP indirect cost in just one application of this phi operator. This requires some non-technical work to show, but I'll gloss over that for now. So then, as I mentioned earlier, the rest of the paper uses this equivalence to ask two questions. First, which classes of cost functions are SLP? And second, for each SLP cost function C star, what is the preimage of that cost under this phi mapping? In other words, what is the full set of direct costs that could have generated it? Now, in the paper, we give some examples of SLP cost functions that suggest that it's a pretty rich class, and we discuss some necessary conditions that are implied by SLP. In the interest of time, I'm going to gloss over those here and just jump straight into the second part of the paper on the UPS model. Okay. So the modern rational inattention literature focuses not quite, but almost exclusively on these cost functions that are called uniformly posterior separable, or UPS. As I mentioned earlier, these were first introduced by Andrew and co-authors, but today are ubiquitous in basically all applications of the rational inattention approach. Roughly speaking, a UPS cost function measures the cost of an experiment by how much, on average, it moves the decision maker's beliefs from her prior to her posterior. And this change in beliefs is quantified by a convex potential function f defined on the space of beliefs, so that the cost of an experiment is measured by the expected change of this potential function from the prior p to the posterior q. So the most familiar example of this is mutual information, which you get when the potential function is proportional to Shannon entropy. Another popular example is where the cost is measured by the expected change in the squared Euclidean distance between beliefs, which is gotten when the potential function is proportional to what's sometimes called the residual variance of beliefs. Another example is what we introduce and call in this paper the total information cost function, which is a weighted average of Kullback-Leibler divergences between state contingent signal distributions, which you get when the potential function takes a particular log sum form. And I should mention in passing that this is closely related to some of Philipp's recent work. So there's a natural connection between the UPS model and our framework, because every UPS cost function is SLP. And in fact, the UPS model is characterized by a somewhat stronger property, which we call indifference to sequential learning. This property says that not only is it weakly cheaper to acquire information all at once than in 2 steps, but in fact, it's equally costly to acquire information in one shot or via any 2-step strategy. And therefore, by induction, it's equally costly to use any sequential strategy that generates a given experiment. The questions that we're interested in are, when is the UPS assumption justified? In particular, how special are the UPS costs within the larger SLP class? And second, what kinds of direct costs could generate a UPS indirect cost? So our 2 theorems speak to these 2 questions respectively. The first theorem says that UPS is equivalent to SLP plus a smoothness condition. In other words, a cost function is UPS if and only if it's SLP and satisfies a differentiability condition that we call regularity. The second theorem then says that UPS costs can only be generated in some sense through Gaussian diffusion sampling. Formally, a cost function is UPS if and only if it's an indirect cost generated by direct costs that all satisfy this property called preference for incremental learning. Now, this is easy enough to state at a high level. What I'm going to do over the next slides is actually give you the formal definitions. This is a bit notationally cumbersome, but the basic idea here is that in many instances, optimal sequential strategies effectively involve taking a continuous time limit where only a very small amount of information is acquired at each step. So this smoothness condition regularity and this other condition on the direct cost preference for incremental learning are defined in some sense in terms of local approximations of a cost function that approximate different types or different notions of a small amount of information. So regularity is going to correspond to the cost of Poisson signals that arrive infrequently but are informative when they arrive, which corresponds to a kind of local first derivative of a cost function. Preference for incremental learning characterizes the cost of Gaussian diffusion signals, which arrive very frequently but are very uninformative in the sense that they induce continuous sample paths for beliefs. And this is defined in terms of a kind of local second derivative of a cost function. So the main implications of these 2 theorems, before I get into details, first of all, are a kind of partial justification for the UPS model. The first theorem, as I mentioned earlier, says that under a smoothness condition, UPS is justified by the optimization inherent in the SLP model. But the second theorem says that the smoothness condition needed to get this equivalence is economically restrictive. So basically adopt it with caution. A bit more subtly, the second theorem says that for any given UPS cost, we can characterize the full set of direct costs that could have generated it through this local second derivative of the indirect cost, which also is the local second derivative of the direct cost. Now, economically, this local second derivative characterizes the cost of sampling from a Gaussian diffusion for just an instant. And once you know how to price, for the UPS model at least, once you know how to price those uninformative Gaussian signals, you also know how to price all other experiments. So basically what this says is that in the UPS model, the fundamental units or atoms of information are precisely Gaussian diffusion signals. Okay, so now on to the details. Theorem 2. For a cost function C star, the following are equivalent. First, it's SLP and regular. Second, it's UPS with a C2 smooth potential function. Now, this smoothness on the potential function is quite innocuous because any potential function can be approximated by such smooth ones. So this characterizes actually a dense subclass of the UPS costs. The more substantive condition is this regularity condition, which is imposed on an SLP cost that a priori does not need to be UPS. roughly speaking, regularity requires that the cost function has a well-behaved first derivative with respect to the experiment. Of course, I need to define more precisely what this means, and that's what I'll do on the next couple of slides. Okay, so regularity is defined in terms of these objects called alpha dilutions, which at least Philipp will recognize. So the alpha dilution of an experiment sigma, which is denoted by alpha dot sigma, is basically the experiment that runs sigma with probability alpha. So think about flipping a coin. With probability alpha, it comes up heads, and then you run a sigma. With probability 1 minus alpha, it comes up tails, and then you don't learn anything. So clearly, when alpha equals 0, this dilution is completely uninformative. When alpha equals 1, you're just back at the original experiment sigma, and the informativeness of this dilution is increasing in this alpha weight. A cost function is regular if, first of all, it's what we call locally linear, which means that, first of all, for each experiment, the cost function is differentiable with respect to this alpha weight at alpha equals 0. This is a kind of directional derivative in the direction of sigma. And moreover, there exists a function on the space of beliefs called a divergence, which roughly speaking is like a distance function between the prior and the posterior, except it needn't satisfy the triangle inequality, so isn't necessarily an actual distance function, such that this directional derivative is equal to the expectation under the experiment of this divergence. Now, such expectations of divergences are called posterior separable cost functions. Not uniformly posterior separable, just posterior separable. So regularity requires this kind of local linearity. It also requires that the divergence in this equation is differentiable with respect to the prior, and that the derivative is jointly continuous in the posterior and the prior. Okay, so what does this actually mean? So first, on local linearity, what this literally means is that the cost function is locally, continuously, and linearly directionally differentiable with respect to the experiment. In other words, you start at a particular point, the completely uninformative experiment, and then you look in different directions, sigma, corresponding to different experiments. These directional derivatives exist. They're continuous with respect to the direction sigma, and they're also linear, which just means that they're posterior separable. This is satisfied in many cases, but rules out particular kinds of kinks in the cost function. Economically, what this means is that the cost of what we might call direct Poisson strategies is posterior separable. Where here you can think of a direct Poisson strategy as the strategy in which you repeatedly run the alpha dilution until success, until you draw a signal. Now, this takes 1 over alpha rounds to get a success in expectation. And so the total expected cost of this strategy is the cost of the dilution divided by alpha. And then when you take the continuous time limit of this by sending alpha to 0, which means that only a very small amount of information is acquired in each period, then you get precisely this directional derivative expression. The second condition of regularity, the smooth divergence condition, is more straightforward to interpret. I'll note that it's satisfied by most posterior separable costs that people actually use in applications, but it does rule out certain things, like the case where the divergence is a metric, because metrics always have kinks at 0.
Alex, just to confirm for myself, is that posterior separable in the sense that we define it in the before, in other words, it has the K, the cost function, but it's allowed to differ across across all priors.
Exactly.
Okay,
so so a different way of defining posterior separability instead of these divergences would be to say that there's a potential function, as in the UPS model, but the potential function can differ depending on what the prior belief is. Exactly. Okay, so this is what regularity means. How do we prove the theorem? there are three basic steps. First, the first observation is that every SLP cost function is what we call dilution linear. And this is a condition that appears in one of Philipp's recent papers. Basically, what this means is that the decision maker is indifferent to the speed of learning, in the sense that if you divide this through by alpha, the cost of acquiring any experiment in one shot is equal to the expected cost of following any Poisson strategy, no matter how likely it is that information arrives in any given period. And this linearity property is just directly implied by the definition of sequential learning proofness. The second step is the observation that given this linearity property, once we have local linearity of a cost function, we can then scale up the local posterior separable approximation to get posterior separability of the entire cost function itself. The third step, which is really the bulk of the proof, is then a calculus exercise showing that if, in addition, the divergence in this posterior separable representation is smooth, then due to a kind of first order condition on this divergence implied by sequential learning proofness, the divergence must in fact be what's called a Bregman divergence, which means that it's generated in this way by some underlying potential function, which gives you the UPS representation that we desire. And this calculus exercise is basically just the gradient theorem or the Poincaré lemma relating path-independent vector fields to underlying potential functions. Okay, so a quick recap. This theorem in some sense rationalizes the UPS model, saying that under a smoothness condition, once you insist on optimization, the UPS model is all that there is. But the next question is regularity just a technical condition? Note that it's being imposed on an SLP cost, which is the output of some underlying optimization process. And there are lots of examples where you can start with a smooth objective function, in this case, a smooth direct cost, and end up with a non-smooth value function or a non-smooth indirect cost. So is this condition really just technical? The next theorem says no, it's economically substantive. And we formalize this again by showing that the UPS model is equivalent to saying that the direct cost is such that the optimal sequential strategy involves observing only Gaussian diffusion signals. And moreover, every such strategy holding fixed the experiment is equally costly. Okay, so how do we get there? We're not the first to note a connection between Gaussian learning and the UPS model. Perhaps the first or best known example of this is in Philipp's paper with Stephen Morris, which revisits Wald's sequential sampling model. And that works as follows. There's a binary state, 0 or 1. The decision maker observes an exogenous Gaussian diffusion signal, the drift of which depends on the true underlying state, and then of course plus some Brownian noise. And the decision maker's posterior that the state is equal to 1 also follows a diffusion. This is a standard result. And the decision maker's flow cost while sampling is given by this flow cost K that might depend on her current belief times the flow variance of her posterior belief. So this K basically represents the flow cost per unit variance in belief movement. Note here that the decision maker isn't choosing what to learn, only how long to observe this process. And the main theorem of their paper shows that this Wald model rationalizes every smooth UPS cost function in the following sense. Take any experiment, any prior, and any stopping strategy that generates the appropriate posterior distribution. The total expected cost of the stopping strategy has a UPS representation where the potential function in that UPS representation has as its second derivative this flow cost K. Okay. And to get there, this is a relatively straightforward application of Ito's lemma. the questions that we're interested in are, well, what if there are more than two states? And what if there are more strategies? What if the decision maker isn't constrained to observing diffusions, but instead can, is completely unrestricted as an R model? And our theorem says that basically there's nothing else. The decision maker, the only way to generate UPS indirect costs is through this kind of diffusion learning. So formally, what this theorem says is under a technical condition on the direct cost that we call local quadraticity, which basically means that the flow cost of Gaussian diffusions is well behaved. Then on the one hand, if the direct cost exhibits this property called preference for incremental learning, then the indirect cost is UPS. Preference for incremental learning means that it's always cheaper to learn via Gaussian diffusion signals than it is to learn in one shot. Moreover, the cost of Gaussian strategies is UPS, just as in the Morris-Strack example. Conversely, under some additional monotonicity conditions, which, as I'll discuss, are more technical than they are substantive, on both the direct and indirect cost, then if the indirect cost is UPS, it must be the case that any underlying direct cost exhibits this preference for incremental learning. So in the remaining time, I want to give you the actual definitions and then give you a quick sense for how the theorem is proved. So this is the local quadraticity. I don't want you to parse the order of quantifiers here. The important thing is that a cost function is called locally quadratic if there exists a continuous matrix valued function of prior beliefs that we call K, or call the kernel of the cost function, such that the cost function admits a kind of second order Taylor expansion with respect to this kernel. So for all experiments such that that are minimally informative in the sense that the posterior belief only moves within an arbitrarily small delta ball away from the prior, the cost of such an experiment can be approximated by a weighted variance of belief movement where the weight on different directions of belief movement is given by this kernel. Okay, so again, this is a kind of second order Taylor expansion. Technically, what this means is that the cost function is locally C2 with respect to the posterior distribution. So for a UPS cost, the UPS cost is locally quadratic if and only if its potential function is C2 and the kernel is given by the Hessian of the potential function. And more generally, this pretty abstract notion of differentiability is actually implied by a standard finite dimensional notion of differentiability with respect to state contingent signal distributions.
So in multiple dimensions, K to be the Hessian of some function is a little bit more restrictive than in one dimension, right?
Yes, that's absolutely right. Let me get to that on this slide. Right, okay, so now here's the main definition. A cost function exhibits preference for incremental learning if, first of all, it's locally quadratic, which roughly speaking, because of this Taylor expansion, means that you can use Ito's lemma to compute the cost of Gaussian strategies, as in the Morris-Strack example. Second, the kernel of the cost function is the Hessian of some convex potential function, which, again, as in the Morris-Strack example, means that the cost of Gaussian diffusion strategies is itself UPS. Now, to Philipp's point, in the case of binary states, this kind of integrability condition on the kernel is without loss. It's satisfied by any kernel that is positive semi-definite, which turns out to be without loss of generality. With more than two states, this is actually a substantive assumption. So there will exist locally quadratic cost functions whose kernels aren't integrable in this sense. And finally, the most substantive part is that the cost of learning everything in one shot is weakly greater than the expected cost of following a Gaussian strategy. So here's the theorem again, a little bit more formally. Let the direct cost be locally quadratic with kernel k. Then first of all, if the direct cost exhibits preference for incremental learning, then its indirect cost is UPS, and the potential function for the indirect cost has as its Hessian the kernel of the underlying indirect cost, or sorry, of the underlying direct cost. Conversely, if the direct cost is Blackwell monotone, suppose in addition that the direct cost is Blackwell monotone, if the indirect cost is UPS with potential function f, and the indirect cost satisfies an additional condition that we call local strong convexity, then the underlying direct cost exhibits preference for incremental learning, and its kernel is given by the Hessian of the indirect cost's potential. So what is this local strong convexity? Formally, it looks like this. Economically, what it says is just the marginal cost of sampling from a Gaussian diffusion for an additional instant is uniformly positive and bounded away from 0. So one thing I want to point out here is that, as I mentioned earlier, for a UPS indirect cost, the full set of direct costs that could have generated it is actually fully determined by the indirect costs, or by the Hessian of the indirect costs potential function. So what this means, again, is that once we know what this Hessian looks like, we can price all other experiments. So in some sense, Gaussian diffusion signals are the fundamental units of information. Okay, so very quickly, how do we prove this and what are some implications? So the direction where you start with a direct cost satisfying preference for incremental learning and derive from that a UPS indirect cost is pretty straightforward. Basically, you start with any sequential strategy, take any given step in that strategy, break that up into smaller pieces by replicating that step using a Gaussian diffusion. By preference for incremental learning, this reduces expected costs. And then it turns out you can get rid of any disposal rounds because of this UPS approximation. This direction of the theorem is closely related to and generalizes the main results in Philipp's paper with Stephen and a related paper by Ben Hebert and Mike Woodford. The difference from Morris and Strack is that they exogenously restrict to Gaussian diffusion signals and for the most part focus on the binary state case. With this restricted strategy space, the main preference for incremental learning inequality has no bite. And as I mentioned earlier, with binary state space, this integrability condition on the kernel also automatically holds. Both of these things are needed in our more general model. Hebert and Woodford consider a slightly richer model than Morris and Strack, but the main difference from us is that they restrict attention to problems in which the decision maker is exogenously constrained to acquiring only infinitesimally informative experiments at each step. And what we show is that basically everything goes through when the decision maker is completely unconstrained. More substantive is the opposite direction, which shows that preference for incremental learning of the direct cost is necessary for a UPS representation of the indirect cost. The key step to proving this is what we might call the kernel invariance lemma, which says that if you start with a direct cost that's locally quadratic and has kernel k, then under some technical monotonicity conditions, it must be the case that the indirect cost is also locally quadratic and has the same kernel. The basic intuition for this is that when you're looking at the cost of an incremental Gaussian signal, because it's only moving beliefs by a very, very small amount, in some sense, it can't be further decomposed into even smaller signals. So this means that any approximation for the direct cost must also translate to an approximation for the indirect cost. Now, that of course is just a loose intuition, but without free disposal rounds allowed in the optimization, the proof is actually not much more than that. The bulk of the proof, and that's also why these monotonicity conditions are needed, deals with the fact that we allow for free disposal. And then once you have this lemma, the proof of the theorem is simple. When the indirect cost is UPS, the potential function is just pinned down by the kernel. So once you know that the kernel is preserved under optimization, you know the potential function and therefore know the entire indirect cost. Okay, so let me take the last 2 minutes to just briefly mention some implications. First, the necessity of preference for incremental learning actually extends to any more restricted optimization problem. So in any optimization where the decision maker can do at least as well as learning in one shot, if the indirect cost generated by that optimization is UPS, then the underlying direct cost must also exhibit preference for incremental learning. So the necessity part of the theorem is quite strong. And the key idea here is that the kernel is invariant under any such optimization. Second, just very briefly, if the direct cost is also locally linear, then we have an easy way to check whether it satisfies preference for incremental learning in terms of its local divergence approximation and the Bregman divergence generated by its kernel. So this is just to say that under some additional conditions, preference for incremental learning is actually relatively easy to check. Okay, so how do we interpret this theorem? Well, preference for incremental learning is probably not reasonable in the following settings. One would be for research and development, where it's very common to engage in strategies where you try to find breakthrough innovations that cause your beliefs to jump by a large amount. It's also probably inappropriate to model scientific research where it's common to try to definitively falsify or verify particular hypotheses. And similarly, in evidence production at trial, where a given piece of evidence might definitively prove or disprove a defendant's guilt. On the other hand, it's possibly reasonable for settings of human information processing, because it's common for psychologists to model human cognition through what's called the drift diffusion model, which is basically as if people are processing information by observing these kinds of Gaussian diffusion signals. And it might also, with some caveats, be plausible in settings of statistical sampling from a large population where your sample size is very large, but the individual observations are very uninformative. Okay, so this is a pictorial summary of what I've said so far. I see we're running along on time, so let me just jump straight to the conclusion. So in the first two parts of the paper, which I've had a chance to tell you about, we introduced these two notions, sequential learning proofness and indirect cost. We show that they're equivalent. We use sequential learning proofness to justify the UPS model, and also show that UPS indirect costs can only be generated by a restricted set of underlying direct costs. In the third part of the paper, which I didn't have time to tell you about, we then push further and look at particular subclasses of SLP costs. Very briefly, there's a property called prior invariance, which means that costs depend on the experiment, but not on the prior belief. This is thought to be important for modeling physical costs of information acquisition, like the equipment needed to drill an oil test well or run a clinical trial. We show that under mild conditions, this prior invariance is inconsistent with sequential learning proofness. This also means that it's inconsistent with the UPS model. An even stronger result is that, except in the case of binary states, no UPS indirect cost could even be generated by a direct cost that is prior invariant, which is significantly stronger than requiring that the indirect cost be prior invariant. And then finally, we look at these two axioms, constant marginal cost and compression invariance, and use these to pin down respectively the new, what we call total information cost function and the familiar mutual information cost function. There are some open questions left by our analysis, which are listed here, but I'll stop here. So thank you very much for your attention. It's been a pleasure, and I'm happy to take questions.
Okay, thank you, Alex. Andrew, Philip, do you have anything to add or ask?
I don't have a question. I do have a comment on how very interesting the various methods that are being used to justify a cost function are, and even the question of the word justify. So there have been, when Sims kind of was introducing rational intention, when you see the Philipp Mateka discuss it, it's kind of, the machine that is learning must obey much of what Shannon said in terms of it being super well designed.
Right.
And that was almost a rationalization for literally entropy as the cost function.
Mm-hmm.
Now we're in another round. I think it's a very valid one and an interesting one in which the process is being explored. And I agree that there's a big distinction between incremental learning of the type you imagine is going on in most psychological cases and drilling an oil well, which is like a fixed piece of capital. The approach that I take, and I have taken in the work that I do, to the word justify, is yet different, which is to justify by properties of data that could be observed. Mm-hmm. And that's kind of the whole reveal preference in this area approach is based on that. The connections are kind of fascinating, and I did not know how much life these ideas had in them and how much there would still be to be done on them, but this is very compelling. Thank you.
Great, thank you.
Okay, Philip, do you have anything to say?
No, I mean, that was super impressive. I would be curious to see the second part, or at least some of it, but I asked many questions already.
Yeah, no, I'm happy to go into the second part if we have time, either now or in the post-recording session. Just chat informally about it.
Yeah, I mean, I guess I don't know. Does anybody want to say something more specific? If not, we can do that for sure. Go ahead.
Okay. All right. So we have what, like 10 minutes?
Yeah, 10.
Okay. I'll try to give a quick overview. Okay. So the third part of the paper, as I've said now a couple times, looks at how this optimization framework allows us to refine or reinterpret some normative axioms that have gotten attention in the literature. This allows us to do a few things. One is to speak to some recent modeling debates in the rational intention literature. Another is to provide a kind of unified perspective on some recent proposed alternatives to the mutual information cost function that have appeared in 2 papers of Philipp's and one of Mike and Ben's papers on neighborhood-based costs. And it also allows us to identify some fundamental modeling trade-offs that applied theorists need to make when modeling costly information. So the background here is that there are what I view as 3 main critiques of the UPS model and of mutual information in particular. The first is what you might call the prior invariance critique, which says that physical or monetary costs of information shouldn't depend on prior beliefs. Mutual information violates this property. Costs do depend on priors. The second is what you might call the returns to scale critique, which says that the cost of producing information should be linear in sample size in the sense that we're familiar with from statistics. Mutual information also violates this property. It is in some sense concave in sample size, so it exhibits a kind of increasing returns to scale. The third, and maybe the most well-known, is what you might call the perceptual distance critique, which in essence says that the topology of the underlying state space should matter. In other words, it should be more costly to distinguish between, if you're reading a thermometer, for instance, it should be more costly to distinguish between whether the thermometer reads 31 or 32 degrees than it should be to distinguish between whether it reads 5 degrees or 50 degrees, because the latter two states are further apart. So with these three critiques in mind, we look at the three corresponding axioms and what our optimization framework has to say about them. So first, with respect to prior invariance, we present two impossibility theorems. The first says that under mild conditions, the only cost function that can be both SLP and prior invariant is identically zero. This basically means that prior invariance either rules out optimizing behavior or means that you're assuming a restricted strategy space. However, our framework also provides a natural resolution to this tension because it's perfectly consistent to start with an underlying direct cost that is prior invariant, but end up with an indirect cost that does organically depend on priors. So we call such indirect costs sequentially prior invariant. Now, in the paper, we have some necessary but not sufficient conditions for what sequentially prior invariant costs must look like. But a natural question is whether any such sequentially prior invariant indirect cost can also be UPS. And the answer is no, unless there are only two states and the indirect cost takes a particular form. This means that generically, the UPS model is inconsistent with prior invariance in an even stronger sense. Second, we look at this axiom that's been introduced by Philipp and his co-authors called constant marginal cost, which basically generalizes the idea from statistics that costs are linear in sample size. And we show that there's a unique SLP cost function satisfying this axiom. And we call this cost function total information. I introduced the functional form very quickly earlier. One potential interpretation of this result is that total information is the normatively ideal cost for information production. And I should mention that we call this cost function total information because a sort of corollary of this characterization is that it is the unique cost function for which only the total amount of information generated matters for costs, but not the process by which you gather it. So it's uniquely process invariant in that sense, and that's why we call it total information. And total information is a particular prior dependent version of what's called the log likelihood ratio cost introduced by Pomato, Strack, and Tammuz. It's also a generalization of what's called the walled cost introduced by Morris and Strack, and in some sense is a finite state generalization of what Hebert and Woodford have called the Fisher information cost function. And so by connecting to these other proposals or proposed alternatives to mutual information, it provides kind of a unified overview or unified perspective on some recent work in this area. Finally, we look at an axiom called compression invariance, which Andrew will recognize as a riff off of his invariance under compression axiom, which basically means that the decision maker has the ability to freely ignore details of the state space that she deems irrelevant. And we show that the unique UPS, or equivalently SLP and regular cost function that satisfies this compression invariance is the familiar mutual information cost function. One natural interpretation of this that we elaborate on in the paper is that mutual information is perhaps the normatively ideal way of modeling the processing of already available information. For instance, when you are internalizing the contents of information that's made freely available to you by an intermediary, such as when reading a newspaper or listening to a news broadcast. And this characterization, it turns out, generalizes, and the proof simplifies a really remarkable and closely related characterization of mutual information in Andrew's paper with Mark Dean and John Leahy. So I'm not going to be able to actually state all of these things fully, but let me, let me try to give the formal statements of the first two at least. So for prior invariance, again, this just means that the cost depends on the experiment, but not the prior. Under mild conditions, the only prior invariant SLP cost is identically 0. These mild conditions subsume any cost function that's strictly increasing in the Blackwell order, any UPS cost function, and also Pomado, Strack, and Tamuse's log likelihood ratio cost. And the interpretation here again is that optimization requires prior dependence, or at least our notion of optimization does. The question is then, can the UPS model be made consistent in a weaker sense with prior invariance, in the sense that the underlying direct cost that generates a UPS indirect cost is prior invariant? Morris and Strack have already shown that the answer is yes, if there are only two states, and if the decision maker is restricted to Gaussian strategies. Our proposition, which is a corollary of our second UPS theorem, says that actually that's the only case. And here's the formal result. The indirect cost must also take a particular form. On marginal cost and returns to scale, instead of acquiring information sequentially, as we've been doing, where you acquire one experiment, observe the signal, update your beliefs, and then acquire another, you could instead imagine acquiring information simultaneously, where you run two experiments that are conditional on the state independent, where you aren't observing any of the realized signals until the end of this process. So a cost function exhibits constant marginal cost if the cost of running two independent experiments together is just the sum of their costs, now evaluated under the same prior, because you're not actually observing signals until the end. This is basically the simultaneous analog of uniform posterior separability, and under some additional conditions, Pomado, Strack, and Tamuse have shown that there's a unique cost function that satisfies this condition. What we show in our result is that there's a unique SLP cost function that satisfies this constant marginal cost. We call it total information. It's given by a weighted sum of KL divergences between the state contingent signal distributions, where the weights are determined both by some parameters and also a linear function of the decision maker's prior. Moreover, under some additional conditions, the only way that this constant marginal cost property can be preserved under sequential optimization is if the underlying direct cost also takes this total information form. This suggests that constant marginal cost typically is not preserved under sequential optimization. So in particular, the indirect cost generated by the Pomado, Strack, and Tamuse log likelihood ratio cost will not satisfy this constant marginal cost. Okay, so I've gone very quickly. I don't want to go too much over time, so I'm happy to talk offline about the compression and variance part, especially with Andrew. But I'll stop here.
Okay, thank you. I think we're also going to stop the recording and begin the informal phase where we perhaps allow people to ask some additional questions and say goodbye at the end.